Today we are going to discuss limit state design. In this we will discuss about the design of flexural members. If you recall, in our last lecture we discussed about the limit state design provisions which are given in code. We discussed about the limit state of collapse and limit state of serviceability. So, some general provisions given in the code IS 456 were discussed about the limit state design. Now, today I shall start with the lecture with a little recall to some important points that I discussed in my last lecture regarding to the limit state of design of flexural members. Now, first let us see what is limit state design. In our last lecture, if you remember, we defined the limit state as a state of impending failure beyond which a structure ceases to perform its intended function satisfactorily in terms of either safety or serviceability. So, two terms are there, safety and the serviceability. So, this limit state talks about the safety of the structure and the serviceability of the structure. Now, structure either collapse or becomes unserviceable after reaching at the limit state. Next, we told what are the limit states. First is ultimate limit state or limit state of collapse. This deals with strength, overturning, sliding, buckling and fatigue failure of a structure. Second limit state is serviceability limit state. This deals with discomfort to occupants caused by excessive deflection, crack width, vibration, etc., and also the durability of the structure. We also discussed about the partial safety factors. There are two type of partial safety factors that are applied, one to the material, another to the loads. These partial safety factors are factors used to modify characteristic strength of materials and values of characteristic load to achieve adequate safety for the design of structure. Now, first let us see what is the characteristic strength of material. If you remember, we defined the characteristic strength of the materials as the value of the strength of the material below which not more than 5% of the test results are expected to fall. Means if we are testing 100 samples, then not more than 5% should show less than this strength, then we call that strength as the characteristic strength of the material. For steel, characteristic strength is taken as minimum yield stress or 0.2% proof stress. Also, we discussed the characteristic loads. What are the characteristic loads? These are value of load which has 95% probability of not being exceeded during the life of the structure, and code, that is Indian standard specifications for the code loads are given in the code. For dead load, IS 875 part 1, imposed load are given in IS 875 part 2, wind loads are given in IS 875 part 3, and seismic loads are described in IS 1893. We also discussed about the partial safety factors, that why they are needed at all. Ideally, what should be the design strength of the materials should be equal to the actual mean strength obtained from the test results. This should be the ideal situation or the ideal condition, and design loads should be taken ideally as maximum possible load obtained from the survey. But because of constructional faults, error in mix proportion, inaccuracies in design assumptions and analysis, we are compelled to use the partial safety factors to achieve adequate safety margins. So, this is the necessity of the partial safety factors that we apply while designing the structures. Now, design values for the materials also were discussed in the last lecture. If you remember, the design value or the strength of the material was defined as the characteristic strength of the material divided by partial safety factor to the material and the limit state considered. Here we are taking the partial safety factor considering the two things, that is material as well as the limit state that we are considering. Looking at the formula, Fd equal to F by gamma m. Here Fd is design strength of the material, F is the characteristic strength of the material and gamma m is the partial safety factor that is to be applied looking into the type of the material and the limit state considered. Now, for the limit state of collapse, this value gamma m is equal to 1.5 for concrete and 1.15 for material. As I just told you that this vary for different material. Here gamma m for concrete we are taking 1.5 and for steel we are taking 1.15. Also for the limit state considered, it changes. Earlier here we have taken the limit state of collapse. Here for the limit state of serviceability, gamma m or the partial safety factor for the material we take as 1 for concrete as well as for steel. Now, design values for loads as discussed later on also. Design loads are equal to characteristic value into partial safety factor. If you look at this formula, Fd, the design load, design value of the load equal to characteristic value F into gamma f, the partial safety factor that we apply on the characteristic value of the load to get the design value of the loads. So, this was just a recall to the important points that we discussed in the last lecture and that are related to flexure. Now, we start with the design of flexural members. So, when we call the word flexure, a structure or the picture that first strike to our mind is a beam. So, what is a beam? A beam is a structural member supporting loads in its transverse direction. The load is coming transverse to the direction of the beam. What is the effect of the load? The transverse load on the beam tries to bend the beam, means the bending of beam takes place. Then what happens? Due to the load here in the beam, bending moments and the shear force come into the picture. So, beam will be experiencing the bending moment as well as the shear force. Now, what is the effect of this bending moment coming to the beam? The bending moment causes internal strains and stresses perpendicular to the cross section of the beam. Now, the two forces will come into the picture when the stresses and strains will be developed in the beam. One is compressive forces, second the tensile forces. Compressive forces will try to shorten the fibers of the beam, whereas the tensile forces will try to elongate the fibers of the beam. So, what will be the overall effect? Whereas the compressive forces are trying to shorten the fibers of the beam and the tensile forces are trying to elongate the fibers of the beam, then overall effect will be the bending of the beam. Now, as you know, concrete is strong in compression and it is very weak in tension. So, the whole of the compressive force we try that concrete should take, means the concrete should take the compressive forces only, because it is weak in tension. So, what should be there to resist the tensile forces? To resist the tensile forces, here we use the reinforcement or steel. So, steel is used to resist the tensile forces and concrete is used to bear the compressive forces that are developed in the beam. Now, think about the material, reinforced concrete material, reinforced cement concrete. It is a composite material that is composed of cement concrete and steel. The two materials are there in RCC or reinforced cement concrete, the cement concrete and steel. Cement concrete, as you know, it is itself a heterogeneous and complex material, because it is not made by a single material. Here we use aggregate, cement and water. So, the behavior of the cement concrete under load cannot be exactly predicted easily, because it is a heterogeneous material and the nature under the load is a complex one. But here we are adding steel also to this material to make reinforced cement concrete. So, now it becomes a heterogeneous material, cement concrete becomes a composite material. So, because of this heterogeneous nature and the complex nature of the cement concrete and also adding steel to it, making it composite material. So, what is the effect here? That the prediction of the exact strength of a loaded reinforced concrete beam becomes difficult and time being. Also, you know that behavior of the cement concrete under load is inelastic from very early stage of loading. So, keeping in view all these facts, the analysis and design of the reinforced concrete sections becomes difficult and time taking. So, to deal with these problems, what we do? We apply some assumptions to simplify our design. And what is the basis of applying the doing the simplification or applying some simple assumptions is the test results or the experimental results that we get. So, from the experimental results on the reinforced cement concrete, we deduce some assumptions to make it simple and easy to analyze and design the reinforced concrete structures. So, let us see what are these assumptions. First of all, the first assumption is that plane sections normal to the axis remain plane after bending. So, if you see here in this figure, this beam made in red color, this is the original form of the beam. It is a simply supported beam. Now, the neutral axis, which is shown by the green color line here, this is the neutral axis. What the neutral axis is? Neutral axis is the axis where there is no strain, means the strain is 0. Now, under the effect of loading or the bending moments applied to this beam, the beam tries to bend this way, which is shown in black color here. So, as you can see, the neutral axis also takes a different from the green one here. Now, above the neutral axis, if you see here in this figure, the fibers of the beam have been shortened under the load, whereas below the neutral axis here, the members in this beam have been elongated due to the effect of the loading. Because of these two, shortening of fibers above the neutral axis and elongation of the fibers below the neutral axis, the bending of the beam takes place here. But here we are taking one assumption that plane sections normal to the axis remain plane after bending. What is the meaning of it here? So, if you see in the original beam, which is shown in red color, you see that this is the end plane, this is another plane. So, these two planes are parallel to each other. Let us see what happens after bending. So, in the black color beam here, which is the shape of the beam after bending, we see this end plane is now inclined, but if you take another plane, if you look at another plane, then the assumption is here that these two planes remain parallel. So, here that there is no distortion in the plane section. So, plane sections normal to the axis remains plane after bending. So, this is one assumption to simplify our analysis and design of the structures. Next assumption is, these are given in code, that maximum strain in concrete at the outermost compression fiber is equal to 0.0035 in bending. If we look at the section of the beam here, from the section you see this is the steel provided in the section, this is a neutral axis. Here if we plot the strain diagram, then the strain diagram is of this shape shown here. At neutral axis the strain is 0. This is the outermost fiber in the compression zone. This is neutral axis. So, assumption is here that maximum strain in concrete at outermost compression fiber is equal to 0.0035 in bending, as shown here, that this extrememost fiber in compression zone will be experiencing a strain that is equal to 0.0035. Next assumption is that we can assume any shape for compressive stress distribution and strain for concrete. If we look at the stress strain diagram of the concrete, then what should be the shape of the stress strain diagram of the concrete? As we know, just I told you that the behavior of the concrete under loading is inelastic from the very early stage of the loading. So, now the question is, to analyze the structures, we should know the shape of this stress strain diagram also. So, code says that the stress strain diagram can be taken of any shape, provided that it should be the area of the curve under this shape should give the results which are in prediction of the strength in substantial agreement with the results of the test. Means you can assume any shape, but the result ultimately you are getting should coincide with the results that we get from the experiments. Means for the design purpose, here we take the compressive strength of the concrete in the structure as 0.67 into characteristic strength. Characteristic strength, you know, we define as the value of the strength below which not more than 5% of the sample should fall when we test these samples. In this figure, the top fiber or the top curve, this is showing, this is the stress strain diagram for the concrete. This first line, this is showing the characteristic strength FCK. As you can see from here, from the figure, the shape of the curve is taken parabolic up to this distance, and this is at this point the strain is 0.002, whereas at the finally we are taking 0.0035 and the stress is FCK. This is the characteristic strength. But for design of flexural members, instead of taking FCK, we take the characteristic strength as 0.67 FCK, because FCK is the lab strength, whereas in actual practice or in the field we are taking this 0.67 FCK as the characteristic strength. Now, we look back that the design compressive stress in concrete FD is taken as 0.67 FCK, the characteristic strength in field, divided by partial safety factor gamma m. Now, the gamma m for concrete is taken 1.5 as you know, then the design strength becomes 0.45 FCK. So, from here we see that the design strength FD for concrete is taken as 0.45 FCK. You can see from this figure that this is the characteristic strength that we take for design for concrete, and after applying the partial safety factor to this characteristic strength, we get this value which is equal to 0.45 FCK, and the shape of the curve remains same because we are dividing this by a constant. From this figure you can see that up to the strain value of 0.002 or you can say 0.2%, the shape of the curve is parabolic. After that it is almost parallel to this axis, and at the final value or the collapse, this strain value is 0.0035 or 0.35%. As we just discussed, that code says, its assumption, simplifying assumption is in the code is that the strain in the outermost fiber in compression zone should be 0.0035. So, that is taken here while showing the strain stress diagram for concrete. Now, we see from here, this is the strain in the outermost fiber in compression zone. This is the section of the beam, this is strain diagram for this section, and this is the stress diagram for concrete for the given section here. So, we calculated that the design strength here for concrete comes out to 0.45 FCK. Now, as you know, this is the neutral axis. So, we are interested in knowing that what is the shape of this stress diagram, where some important values lie. Here from this stress diagram we see that certain upper portion of this stress diagram is straight line, after that this is parabolic. So, this has been taken from the stress strain diagram that we just saw from this figure. In this figure also, if you can see, this portion is parabolic, after that this is horizontal line or straight line. So, from there this is taken that this stress is varying in a straight line up to certain portion, and after that this is parabolic and the value here is 0. So, at neutral axis the stress or the strength, compressive stress or the compressive strength is 0 here at the neutral axis. So, compressive stress is 0 here, and here at the outermost fiber this is 0.45 FCK. Now, we are interested to know these values, that up to what depth this is a straight line and up to what depth this is parabolic. So, we can know this depth from this triangle, from these two similar triangles. If you see these two triangles, this bigger one and this smaller one, these are two similar triangles. So, from the property of similar triangles we can write that 0.0035, this value divided by 0.002, this value will be equal to xu, this depth means the depth of the neutral axis, divided by this much depth. So, here out of these 4 quantities, 3 are known and 1 is unknown. So, this can be, this unknown quantity, this much can be calculated from the similar property of the similar triangles, that 0.0035 divided by 0.002 will be equal to xu divided by this distance. So, if you solve this equation, then you will get that this value or this depth you will get as 0.57 XU, which is in terms of the depth of neutral axis, means 0.57 times the depth of the neutral axis XU. The portion which is parabolic is up to a depth of 0.57 XU. Now, this portion you can get simply by subtracting this 0.57 XU from XU, then you are left with the value 0.43 XU. This is the stress diagram for the concrete in compression zone, and as you know, in tension zone we neglect the concrete because concrete is very weak. this shape is not a straight line, this is a curved line, and this gives the characteristic strength. Divided by this partial safety factor, we get the design value. And here how we get the characteristic value or the characteristic strength? What we do, that for very initial portion we get some straight line portion. So, parallel to this, at a strain of 0.2%, parallel to this line we draw a line, and where it strikes, that value we take as the characteristic strength Fy. Now, code says that maximum strain in tension reinforcement in the section at failure shall not be less than Fy divided by 1.15, that is the partial safety factor, into Es, the modulus of elasticity, plus 0.002. This is all about some important assumptions and some important point that we need in the design of flexural members. In next lecture, I will deal with the design of singly reinforced beams. Thank you for the patient listening. Thanks.